So I'm going to go to a question that was sent to us by Rashford Mutlala. Rashford sent us a cubic that is already sketched. We just saw an example where we had to draw. And shout out to you guys for sending us those questions. We really appreciate your presence and watching the show and also informing others to watch the show. Shout out to Lewe as well. We see there's a lot of questions that you guys send here. My next question is going to be from Lebohang Maditi. That's what I'm going to do. I hope those two will just take us to the end of the show. All right, so Rashford Mutlala's question, and if we have time, we're obviously going to squeeze more because I've got a lot of them that you guys sent to us here, so we'll keep checking if we have time. So this one looks as follows. We are given a function of f of x, right? It says here, we're given f of x, which is equal to x cubed, okay? And then it says plus bx squared. Woo, problems begin right there. Plus cx plus d, right? Apparently, this is drawn on the same set of axes with another graph of g, which says g of x is just as easy as 2x. Okay, so we obviously know the first graph, the graph of f, is a cubic, and the second graph is a straight line that is passing through the origin. You need to see this once you start looking at the given information. So let me try and get you the picture of what we're dealing with here, right? I'm going to try and get you a picture of what you're working with here. Let's draw the cubic graph like this. Okay, here's my cubic graph, as ugly as I can get it to look. Okay, then there is a straight line which I'm going to draw in a different color. Let's use yellow for the straight line. I'm going to use a yellow color for the straight line. And these beautiful graphs are apparently meeting each other at some weird number here. Okay, fine. So let's get the Cartesian plane now. I'm going to get the Cartesian plane for us here quickly. So our Cartesian plane passes through some point here, yes. So it actually looks like this. Okay, that's the x-axis, and we're obviously going to need the y-axis somewhere there. Ah, great stuff, great stuff. Ah, perfect, right. So this is Rashford's question. Okay, Rashford, this is the y-axis, this is the x-axis. There's another line here, the blue line, which I'm going to add, which apparently is from point P at the green graph to point Q here on, not at, but on the yellow graph. That is actually going to give us a straight line PQ, which happens to be perpendicular to the x-axis. So this is essentially what you're looking at. The extra info that was given to us is that the cubic graph cuts x at -2. It also cuts x at 1. And it also happens to cut x at 3, right? And we don't know much about where the g of x graph passes, except that it's obviously passing through the origin, so it's passing through 0 and 0. That will be the graph of g. Beautiful stuff. So this is my f of x graph, and obviously this is my g of x graph. Okay, we've got all that was given to us. So the first turning point here, which is this point here, is point A, and the second turning point is this point here, which is point B. Those are turning points. Because I've shown you how to work with the turning point, I'm going to be very selective when I do these questions to help you understand without repeating stuff that you already saw how to work with. So the first one here says to us here, we need to show that the equation of f of x can be expressed as something. So we have to find the equation. They say show, okay, f of x can be expressed as x cubed, okay, minus 2x squared minus 5x plus 6. So that's what they want you to do. Okay. Now, in this case, I am being asked to find the defining equation of the graph. And I want to draw your attention to two possibilities. Scenario number one is if you've got the x-intercepts, right? If you have x1, x2, and x3, and some random points, which is given by the x and y coordinate. How do you find the defining equation in this case? Well, you're going to use y is a into x minus x1, x minus x2, and x minus x3, where your x1, x2, and x3 are the x-intercepts of the graph. You're going to sub those there, right? And then you will take your x and y and substitute this number here and that number everywhere where you see x and everywhere where you see y to solve for the value of a, and that should lead you towards finding the equation of the graph. Sometimes your graph bounces, which means it has got an x-intercept that happens to be a turning point. It does something like this. So when this happens, you guys need to know something very exciting. It only has two roots, x1 and x2, right? Where the second one, where the graph is bouncing, is a repeating factor. If this happens, you know that your factor here is a repeating factor. I call it the bouncing point. So it means your graph will be a into x minus x1 into x minus x2 twice. Because at that point, the graph is repeating. It's x minus x2 and another x minus x2. So it's two of them happening. Now, if it happens that they give you maybe the turning points, then you obviously need to engage the concept of finding the derivative first and then working with the derivative. But these are the popular ones that you might get, popular scenarios. Scenario 1, given the roots. Scenario 2, given only 2 roots and some random point. Of course, there has to be a random point that they're giving you to help you to figure out the solution, right? Obviously, this guy will come here, not there, but here by x1, and the second one, the repeating factor, the bouncing point, where the graph bounces will come here because that point is actually appearing twice as far as the factors are concerned, right? And then the random point will obviously go for your x here and your y. Then you can solve for your a and then be able to play around with a lot of very exciting things here, right? Now, if they give you scenario number 3, a cubic, and they only give you the turning points, they don't give you anything but the turning points. They give you the coordinates of the turning point, an x and a y here, and they give you an x and a y here, right? You need to understand you have f of x, which is ax cubed plus bx squared plus cx plus d, which is the defining equation of a cubic. You will need to work out the derivative, right? Which is going to come out as 3ax squared plus 2bx plus c. And you're going to need to equate it to 0 because at the turning points, right, the derivative is 0. And then you can then substitute those x values. More often than not, when you substitute these x values to solve for a, b, and c, you're going to have a situation where you deal with simultaneous equations. But that's the approach of working out the defining equation of a cubic graph under these 3 scenarios. Please keep that in mind. So let's check the one we are basically dealing with in this question. You will agree with me that the one that we are faced with here, Rashford, is a situation where you are given the x-intercept. You have them. You've got x of minus 2, 1, and 3. So this simply means my approach to finding the defining equation is going to be initiated by saying, examiner, y has to be a into x minus x1, x minus x2, and x minus x3, because those are unique x-intercepts. 3 unique x-intercepts we see on our graph without any complications, right? This is how you're going to begin your working, right? Now, this is where a lot of people will then struggle. What do we know here? I'm going to replace my x1, x2, and x3. So I've got y equals 2, right? I have got x, okay? There's a minus 2 there. When you're writing minus of a minus, it's going to become plus 2. Please keep that in mind, right? Okay, there's another x here, and there's another x. I'm going to replace my x1, x2, and x3. The first one was minus 2 there. It's going to change to plus because minus of a minus is positive. And then the next one is minus 1, and the third one is minus 3. Those yellow numbers come from the x-intercepts. No complications. Now, the other thing that could have put you off, that you could probably wouldn't have noticed, is that the a value was given in the opening statement, Rashford. Your f of x comes with a already. The coefficient of x cubed is already 1 because there was nothing written here. So you might make a mistake of not knowing that your a is already 1 because this is normally what we put for a. So a is 1. So I'm going to come here and then say, okay, fine. My a was 1 also. It was given in the opening statement on my graph of f of x. Then the rest is just to multiply these things out, algebra again. Algebra, algebra. No complications. Now, it turns out that when you're multiplying these kinds of things, you're dealing with 4 things here. I'm dealing with 4 things. It is 1, the first bracket, the second bracket, and the third bracket. So those are the 4 things I'm dealing with. In math, you can only multiply 2 things at a time. That's what we are actually going to do. So I'm going to multiply these 2 together. And I'm going to multiply these 2 guys together. So 1 times x is going to give us x. 1 times 2 is going to give us 2. I'm going in here, right? I'm going in here. Okay, now when I multiply the second bracket with the third bracket, x minus 1 times x minus 3, I'm going to end up with x squared, and then minus 3 minus 1 is going to give us minus 4x. Negative times negative is going to give us positive 3. Right, so that is my f of x so far, which I can then clean by removing those brackets by multiplication. X times x squared is x cubed minus 4x squared plus 3x. And then we've got plus 2x squared. And then we've got minus 8x. And we've got positive 6 when you multiply 2 and 3 at the end. I'm just removing brackets, something that you guys are very good at. And then in conclusion, we can just wrap this up and say, examiner, therefore, we can conclude that f of x is just given by x to the power of 3 minus 2 and 4 are what we call like terms. This guy is friends with that guy there. Minus 4 plus 2 is going to give you exactly minus 2x squared. 3 and 8 are friends as well. So if you are working with this guy here and that guy there, 3 minus 8 is going to give you minus 5. So you're going to be left with minus 5x. And 6 is a loner. So we have your function of f of x, which is exactly what the examiner was asking you to find in the opening statement. Find f of x if you are dealing with a situation where the roots are given. It does in fact amount to x cubed minus 2x squared minus 5x plus 6. Right. Now the second part of Rashford's question. Let's go to the second part. The second part says, okay, now we need to find here say the graph of f is concave down for x. Okay, cool. Let's go to that. Right. It says f of x. Okay, fine. Yeah, okay, they say calculate coordinates. Okay, coordinates of A and B. Before we get to this one of concavity, right? So when you're looking for A and B, you're gonna check what is A and B on my sketch. The opening statement told us that A and B are the turning point of the graph or the stationary point of your graph. You know now that at the turning point, the derivative of the graph is 0, the gradient is 0. So you do two things. You find the derivative, you equate to 0. After that, you just solve. The rest will just be grade 10 algebra, no complications. Right. So let's go back and check where A and B is. A and B are the turning points of the graph. So the examiner is asking us to find the coordinates of the turning points. Let's impress this examiner and show them that we know what is going on. So let's start our process of finding turning points. For turning points, step 1, you find the derivative. So x cubed minus 2x squared minus 5x plus 6. So let's go f prime of x, the first derivative. Right. First derivative is coefficient times exponent. You get 3x squared. Negative 2 times 2 gives us minus 4x. 1 times minus 5 gives you minus 5x to the power 0, which disappears. The derivative of a constant is always 0. So like I said, 1 mark for derivative. Where is my second mark? My second mark is what you get when you take this 3x squared minus 4x minus 5 and you equate it to 0. That is where we're going to allocate you the second mark for knowing that at the turning point, the graph is not increasing or decreasing. It has a gradient of 0. Very important. Now from here, you can use the quadratic formula, or you can complete the square, or you can factorize. Stay away from completing a square. It's long and laborious and time consuming. Rather use the quadratic formula. It's quick. Or factorize. Let's take our chances. Can we take our chances? Yeah, turns out we can't. Okay, cool. So I'm going to have to use a quadratic formula. X is minus b plus minus the square root of b squared minus 4ac, right? Everything divided by 2a. Okay. And then I'm going to then say minus 4 plus minus the square root of minus 4 squared. Minus 4 into my a value is 3 and my c value is minus 5. All these need to be divided by 2a, where my a is equal to 3. Then you go to your calculator. Remember, your calculator is an instrument, not a monument, so you people must use it. So there's a negative, open bracket. My b is a minus 4. Please be careful with the signs. Minus b plus, and then the square root, open bracket, that negative 4. If you don't put a bracket there, the whole thing is going to be wrong because your calculator is not going to do what you want it to do. Please use parentheses. Please, 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 beautiful people. So minus 4 squared, and then minus 4 into my a value is 3, and my c value happens to be negative 5. All these need to be divided by 2 times something beautiful, which is 3 in this case. And then the answer comes out as 2 plus the square root of 19 over 3, right? Which is 2.11. So 2.11 is the first x value, or x equals 2. Now, because I know I'm going to need this x value, I'm going to be very naughty and substitute this in point B, because if you look at this, we're getting a positive value of x. It is positive 2.11. Which one of those 2 points is it likely to be? 2.11. Look at the Cartesian plane. The positioning of A is on the left-hand side of the y-axis, so we expect the x-coordinate of A to be negative. So since I got 2.11, I'm expecting that to be for B. I'm expecting that to be the x-coordinate of point B. So that 2.11 is going to be the x-coordinate of B. We don't know what the y-coordinate is. So now let's find the x-coordinate of the other one. But before I do that, I'm going to teach you something very nice, a nice technique. There are a lot of letters or variables, or actually there are storage compartments in your calculator that you see. All the red numbers, A, B, C, D on that calculator that you see, all the way up to M. Those are storage compartments. So I want to store this number of 2.11, which is not 2.11 but 2.12. I didn't round off correctly. 2.12. Let's fix that. Right, 2.12 when you round off to 2 decimal places. Okay, beautiful stuff. So I'm going to also fix it right at the bottom. I'm going to go back to my calculator and check that out. I got an answer of 2.11, which I think I'm going to need to use to figure out the corresponding y value. Remember, when you want to work out what is the corresponding y value when x is 2.11, you're going to need to substitute that in the original equation. So because I know I'm going to need it, I'm going to store it inside B. How do you store it? You can store it inside any one of those letters, by the way. So you're going to press Shift, and then you're going to press Store, which is on the RCL button above 7. Shift, and then you press Store, and then you select the letter you want to store that number in. So I want to store it inside B, so I'm going to push B without pushing anything. So that's the algorithm of storing numbers. I pressed, first of all, Shift, and then I pressed STO for store, and then I pick any letter that I want, right? Any letter that I want. In this case, I picked B. Right. So that means you'll see your calculator says your answer has been stored inside B. When I need to use that 2.11, I'm just going to call B back. Okay, cool. And then now I'm going to go back to my calculator and press the back button. Okay, AC, and then press back, because remember we're doing a quadratic calculation here. We have to find the other answer that you get when you're not using plus, but when you're using minus in order to get the coordinate for A. What do you get there? You get an answer of negative 0.79. Negative 0.79. Okay, let's go back and put that on our graphs there. Let's see what will happen. It's actually negative 0.79. So my x is negative 0.79. I don't know what the corresponding y value is at point A, but that means that, beautiful people, I'm going to need this in order to find y, so I'm going to store it. I'm following my algorithm. Shift, store, letter. My letter, in this case, I want to use A. So I'm going to press Shift, then I'm going to press Store, then I'm going to press A, which is there by the minus button. Calculator says your answer has been inserted inside A, so I can press AC. Even if you switch off your calculator and you come back, your answer will always be stored in that particular solution that you have there. No complications. Now that I want to now replace, remember, when you've got x's, you want to find the corresponding y values. Let's go back and say we found that the second x value is negative 0.79. We want to know what is f of 2.12. Remember, we said this is 2.12 to 2 decimal places, so we need to make sure we round off correctly. We're going to find the answer there. Or what is f of negative 0.79? Remember, you substitute back to the original function, not to the derivative. Take it back to the original. Now check what I'm going to do now. Check what I'm going to do. This is actually very nice. When I substitute in order to figure out the corresponding y values for B, I know that the answer for B has been stored inside the letter B. Instead of x on my cubic is x cubed minus 2x squared minus 5x plus 6. I'm not going to use x, I'm going to use B. So I'm going to say alphabet. If you want to use anything red, if you want to call it, if you want to use it, you press alpha first. So I'm going to say alphabet B cubed, right? Minus 2 times alphabet B squared minus 5 times alphabet B. This saves time. Plus 6. And then I press my calculator to see what the answer is going to come out as. It comes out as minus 4.06. Minus 4.06. So this is going to be minus 4.06 as the corresponding y value. And then I'm going to go to the second one for alphabet A now. I know that in point A, the x coordinate is minus 0.79. I want to find the corresponding y value. So we need to substitute into the original. But we want to substitute what answer? The answer inside alphabet A. If you press equal to, you will see the answer inside alphabet A is still negative 0.79. So I want to use that and replace it for x in my cubic. So I'm going to say alphabet A cubed, right? Minus 2 times alphabet A squared minus 5 times alphabet A plus 6. And then you press the equality sign, you end up with 8.2. That's what you're getting. Right, I'm going to get an answer of 8.20 here. 8.20. So those will be the coordinates of point A and point B. Beautiful stuff. No complications at all. It's absolutely exciting. The last part of this question that Rashford wanted us to look at is they're asking us to find the point of inflection. And they're asking it in a very sneaky way, right? They're asking it in a very sneaky way. Okay, we found the answers to those. We're not going to entertain that now. We have them on the Cartesian plane as well. See Cartesian plane for this. I'm actually rushing for time, guys. Let's start and find the solution to the last question of Rashford. It says here, the graph of f is concave down for f is concave down for x is smaller than k. Find k. Okay, concavity, concavity, concavity. A cubic graph changes concavity. A parabola does not. For example, this parabola is concave up. This parabola is concave down forever. A cubic does this, and then it changes and does that, right? So it changes from being concave down to being concave up. So we are interested in finding at what point does the graph change its concavity? Where does it change from being concave down to being concave up, or the other way around? That's what we want to know. And that point has a special name. We call it the point of inflection. That's where the graph changes concavity. Beautiful stuff. So let's go back and try to put it nicely for you, right? The graph will be concave up, where the second derivative is greater than 0. And your graph will be concave down when the second derivative is less than 0, right? Now, which one of these two is the examiner interested in? Remember I said the graph changes concavity at the point of inflection, the point of inflection. And in order to figure out the point of inflection, you're just going to use the second derivative equated to 0. I wish we had more time to explain more of those, but we're going to get more shows again in future. We'll obviously get these kinds of questions again, and we'll get time to re-explain what is going on. So the examiner says f is concave down for all x values smaller than 0. So which means the examiner is interested in that. So I'm going to go and try and find my f and find its second derivative in order to find where it changes concavity, right? Let's go and find that. Okay, right. And if I go back to my graph, let's go back to the sketch so that you guys will have an idea of what is going on. There's a point where the graph is going to change concavity, right? Before that, right? Before that, there's parts where the graph is just concave down. From the left to the right, our graph starts by being concave down. It starts by being concave down. It starts by doing that, right? Concave down. And then there's a point where it changes concavity and starts being concave up, right? Concave up, right? So those are the two things we're interested in. We want to know where is this, because apparently that's where it's going to change its concavity, right? Let's figure that point out. Okay, our cubic was given to us as f of x equals x cubed minus 2x squared minus something very exciting. It was minus 5x plus 6 if I'm not mistaken. And then you're going to find the first derivative of this, which is going to be 3x squared minus 4x minus 5. But we don't stop there. We then find the second derivative. The second derivative we should get by 6x minus 4. Now that's the second derivative. If you take the second derivative of a cubic and you equate it to 0 of any graph, right, you're going to be finding the point where the graph is going to be changing concavity. But we don't want that. We don't want that. Remember, we don't want to know where the graph changes concavity because we were told that it changes concavity when x is equal to k. Where what we are going to do is we are instead going to take that 6x minus 4 and put it less than 0 and then solve for k, which means we're going to have 6x is less than 4 because I told you for concave down, you equate we just put the second derivative less than 0. And then if you simplify this further by dividing both sides by 6, you're going to get x is smaller than 2 divided by 3. So that means k is equal to 2 over 3 because they told you that it changes concavity and it is basically going to start being concave down from points where x is smaller than 2 over 3, right? Where x is smaller than 2 over 3, which is that k value, x less than k. That's where the whole story of concave down applies, which means if you go back to the drawing and we check that, we can claim that 2 over 3 is something small, somewhere here, right? Let's use 0, somewhere here, the graph changes from being concave down and being concave. That point is the point of inflection. They didn't really want the corresponding y value. If they did, you just take that x value. If they want the corresponding y value, take that x, substitute back to the original. It's always back to the original, not to the derivative, not to the second derivative. Back to the original. Every time you have an x and you want the corresponding y value, just take that x, replace with whatever your x you had on the original. Substitute in the original equation. Very powerful concept that we learned from grade 8 and grade 9. Absolutely, absolutely exciting. Okay, cool. Yes, that's it. Now, because this is Tenfold Live, and I know you guys are people who are interested in knowing very interesting things that involve your graphs and those kinds of things and different methods. Here's a beautiful method of finding the point of inflection. If I have a cubic that looks like this, right? If I have a cubic that looks like this, it obviously has a turning point at point A, which we did see, and it also has a turning point at point B. Now, it's actually a known secret that the point of inflection that I'm busy telling you about is exactly in the middle of your turning points. Very powerful. In the middle of the turning points. Now, this means, beautiful people, if I wanted to find that without using a second derivative, I could have just find the midpoint of the turning point, which means we could have just said the x value of the point of inflection is the x at A plus the x at B divided by 2. This comes straight from your knowledge of analytical geometry, how to figure out something that is between two things, right? Now, because I already have my A and B stored in my calculator, remember I stored them in my calculator, I'm going to call a fraction, and I'm going to say alphabet A plus alphabet B, because those two alphabets are holding my x values at the turning point, divided by 2. We are looking for the average. And look at what we're getting. 2 over 3 comes out as the correct answer. The 2 over 3, which confirms that this idea does in fact give you the same answer as the one that you were looking at. Very powerful indeed. I hope this has helped you to understand what is going on as far as working with a cubic graph is concerned.